Alright, so when we just covered the third law, we said that no force exists in isolation. So what I want to present to you is that this scenario here where you got a box here, we do a box, and then this planet Earth here, and the box is going to be falling downwards. So, you know, you could look at it like that, you could look at it even much closer to the surface like this, and what you're going to see is that, you know, we'll give our box a mass of 2 kilograms. We'll see that this is moving down, and we know why it's moving down, right? It's moving down because you've got a force of gravity acting on this box. And it's not just moving, it's accelerating. So we easily have the ability to know how large that force is just because we know what the mass is. 2 times 9.81, that gives us 19.62 newtons of force acting in the downward direction. Now what we're going to do is we're going to state who's doing the force and who's on the receiving end of the force. The Earth is applying this force, so I'm going to call it force of gravity Earth on box here, E on B. And subscripts will help you keep track of what's doing the applying, and it'll also help you keep track of action-reaction pairs. So there's a 19.62 Newton force acting in the downward direction on this object here. It's 2 kilograms, so when you do the math, if you apply the second law here, sigma F equals ma, our only force is the 19.62, and then you have 2, and then our resulting acceleration, you're just going to get 9.81 meters per second squared for our acceleration. We know that's the rate at what things fall, but the weird thing is now when we consider the action-reaction pair that's occurring, that's a little more out there in terms of, you know, what we're looking at. So we said no force exists in isolation, and if the Earth pulls the box down, the third law states that the box simultaneously has to pull the Earth upwards. There is a force being exerted on the Earth, and it's also a force of gravity. All objects have their own gravity, it's just that the Earth has a lot more gravity than we do. And then we're going to call this box on Earth. So there is actually a force of gravity coming from the box, acting on the Earth, trying to pull the Earth upwards right now. And both of these forces are 19.62 newtons. So what we're going to see is that there's a 19.62 newton force down. There's also a 19.62 newton force up acting on this other object, that object being the Earth. And it will actually move the Earth, but people don't usually want to believe that. They just look at it, they say, no way, not possible. You can't have such a small object move such a large object. And we'll see why you would never be able to observe that, but it's got to be true according to the laws of physics here. So when we do the second law on Earth, we can do sigma F equals ma. Now we know that there's only one force acting on the Earth in our view right now, 19.62 newtons up. That force of gravity right there. But the Earth has a lot larger mass than the 2 kilogram box. The Earth's mass is 5.97 times 10 to the 24 kilograms. So when we go to solve for our acceleration, we're going to get a much larger value than the force of than the acceleration acting on the 2 kilogram box. So when we do the math here, 19.62 divided by 5.97 times 24, I'm going to get a really small number. In fact, it's going to be reported in scientific notation. I get like 3.29 times 10 to the negative 24 meters per second squared. That's our acceleration. So the Earth is accelerating upwards during this event, but it's at such a small, minuscule rate that this would not even be measurable. We basically only have equipment to measure out to maybe 10 to the negative 10 meters per second squared. So nothing that slow could actually be detected. But we do have other objects, bigger objects like other planetary bodies that can move the Earth more significantly, so we can prove it that way as well. But it's very interesting that such a small mass can still have somewhat of an effect on Earth, even though it's not observable. So that's the third law in action for one very small mass and one incredibly large mass.